Okay, so this is topic 8, part 3. And we're going to talk about absolute maximum shear stress and then do a couple of examples and kind of wrap up this topic on plane stress transformation. Okay, so again, I'm going to remind you guys that when we're dealing with stress, we have those normal stresses and then we have two shear stresses on each face of our element. This is for a 3D element. But then plane stress, we can develop our stress transformation equations to determine the normal and shear stress acting on any skewed plane of the element, and we can do that using Moore's circle in a pretty simple manner, okay? We can also determine the unique orientation of an element with only principal stresses acting on the faces, which we did in the previous couple of examples. And in general, these principal stresses have magnitudes of maximum, intermediate, and minimum intensity, and we call this triaxial stress. So tri would refer to those three, and those three values are the maximum, intermediate, and minimum intensities. So we're not going to actually be discussing 3D stress transformation. This could be in a different class if you end up taking it, but that's going to go into the theory of elasticity. And for this class, we're only going to discuss that plane stress transformation. Okay, but we are going to talk about absolute maximum shear stress in that regard. So let's consider a material subjected to in-plane principal stresses, sigma 1 and sigma 2, like this teeny tiny figure I have up here. So you see you have the sigma 2 acting in this direction, sigma 1 acting in this direction. And if we wanted to isolate those, if we wanted to view them in 2D, we can see that we're going to view all three of those planes, so the x, y, y, z, x, z over here, and we can see what's happening with each of those stresses. And then we can use Moore's circle to determine the maximum in-plane shear for each case, and then we can determine the absolute maximum shear, not just within a certain plane, but of the element entirely in the whole material. Okay, so these are two different things that we're looking for. I should actually put in max in-plane shear for each case, and then the absolute max shear stress. Those are both two very important things. Okay, so what is absolute max shear stress? This should be when sigma 1. When sigma 1 and sigma 2 have the same sign, okay, what happens here, you can see what I mean by that is that both of them are drawn towards the positive sigma here. This would be positive sigma. Okay. So when both of these, I don't know why this arrow is so thick. Let's read that. There we go. When both of these are positive, so our sigma 1 value and our sigma 2 are drawn to the right of this sigma axis, when they're both positive, we have our max shear stress as sigma 2 over 2. And for all three circles here, so we're going to draw one circle for the entire system, one for sigma 2, and the remaining for that sigma 1 minus sigma 2. And we can get the max in-plane shear stress as this guy right here. And this value is just max in plane, so this is just per plane. But if we want the max absolute, we can use this formula right here. Okay, and this is only for if sigma 1 and sigma 2 have the same sign. But when we start drawing the circle, I'm going to refer to this less, because really, if you just look at the circle, you'll know how to add these and subtract these and divide these together to get the right value. You won't need to necessarily think so much if they're positive or negative, but this is just kind of something to go back to in case you're a little bit lost. So I'll show you that in the example, it's not the biggest deal to recognize it. Again, this is sigma 1. So now, here, this is if sigma 1 and sigma 2 have opposite signs. So what happens here is sigma 1 is measured from the right of the axis, sigma 2 here measured to the left because it's negative, and now we'll take sigma 1 minus sigma 2 divided by 2 to get the absolute maximum. And this is when we have opposite signs for sigma 1 and sigma 2. Okay. And these are just some important points that you can come back to if you want to look through these summaries before we do the example, okay? So let's attempt this example now, and you'll see how simple this is if you just kind of look at the geometry of what's going on, okay? So the first thing we want to do, as usual from before, we want to determine what our principal stresses are. And actually, let's read this problem first. So we have a point on the surface of the cylindrical pressure vessel, and it's subjected to the state of plane stress that's shown in this little element, we want the absolute maximum shear stress at this point. So the first thing we want to do is determine the principal stresses. Okay, and that's going to be sigma 1, which is going to be the larger value, sigma 2, which is going to be the smaller value always, so I'll put here. Okay, and these, we're just going to plot them along our sigma axis. Okay, let me come here. Since they're both positive, I'm going to go ahead and draw both of them in the positive direction. So here we'll say is sigma 1. Well, this is the sigma axis actually. Okay, that's our sigma 1. Usually I like to draw the circle before because I have, okay. And then our sigma 2, our 16 MPa, is going to be the radius of the inner circle. So if this is 32, then 16 would be right, I'll do a different color here. 16 would be right in the middle, which would mean we'll get two other circles out of this, both with, this is just like that. Okay, okay, this is really bothering me because it's so crooked. Okay, the best I can do. Now what we can see here is if the diameter from here to here is 16, that means the radius, right? The radius of this is 8. Okay, the radius of this is 8. Then the radius of the larger circle is 16. Right, 16. Then we can see here basically that our absolute maximum tau, the highest value that this whole element reaches, this would be our tau max absolute. And that would just be the 16, the radius of the larger circle. Okay, that's pretty easy to just look at like that. And you can also just use that formula. So when both are positive, the formula, if you wanted to use the formula, is just sigma 1 over 2, the radius of the big circle. So you get the same value. I think it's a lot easier just to look at the circle and look at the tau axis and see where the absolute is and having to remember any formulas. So you guys can do either one, which kind of works for you. But now to get tau sigma average, all I'm going to do is take this 32 plus the 0 divided by 2, and I get again that 16 MPa. Okay, so you can get both of these either by looking at the circle, or you can get them through the equations. Okay. Now we want to look at the max in-plane shear stress just so we can see what's happening there. So let's just see, just as a side note, for max in-plane, and we can determine this using Morse circle drawn between this 32 and 16. So we can see here that max in-plane is just going to be that 32 minus 16 over 2, which is that 8, which we get from this right here. You can see that the tau for any one plane, since they're equal, it doesn't matter which one you choose, they're both the radius of 8. So the max here, max of any specific plane, not the, so this circle represents the entire, these are specific planes. Okay. And then here, our sigma average, again, is going to be that 32 plus 16 over 2, so we get 24 MPa here. Okay, so that's how we could find max in plane versus max absolute. And this was actually the answer here. This is what they were looking for. Okay. Okay, now let's move on to example 11. So here, due to an applied loading, an element at the point on a machine shaft is subject to a state of plane stress. Determine the principal stresses and the absolute maximum shear stress at the point. So first thing, this is still pretty simple. It's a little bit different. So the first thing we can do is let's figure out our principal stresses. So I'm going to start here. Okay, so, okay, before we do this, let's first draw Moore's circle. And from Moore's circle, for Moore's circle, we need the center. So we can get that sigma average equals negative 20 plus 0 over 2. We get negative 10. And then our reference point, which would be that A, would just be the negative 20 comma negative 40 that we're given from this here, like before. And then we can get the radius of our circle as the square root of 20 minus 10 squared plus this Pythagorean theorem again. So this should be pretty straightforward now after the last couple of topics where we kind of went over this a lot. Okay, and now we're going to go ahead. Let me draw the circle first. It's usually easier. Okay, now I know that my sigma 1 is going to be, let's see, if the center of the circle is at negative 10, 0, that means that this center has to be drawn to the left of my axis. Okay. Okay. And this is, again, this is my sigma, this is my tau. And this is the center here, which is negative 10, 0. And I also have my reference point, A, which was negative 20, 40. So I need to come out another negative 10, up 40. And this is A. And here, this is how I can figure out the radius. Because here, this length is 40. And then from C to A here, this would have been 10. And that's how I get the 41.2 here. And then, of course, we know that this here, this angle, is my 2 theta. Okay, I think we've written everything. And then we know also that our principal stresses here are going to be the sigma 1 and sigma 2. So things change a little bit when our sigma 1 and sigma 2 are not both positive. When they're both positive, you can pull them out directly from the picture that you're given. But when they're not both positive, we have to plot them first and then figure out what they are. So here, our principal stresses for the circle, sigma 1, is going to be that negative 10 plus the radius, 41.2. So we're given 31.2 psi. And our sigma 2 is going to be our negative 10 minus 41.2, which is negative 51.2 psi. And this is the first part of this answer here. So principal stresses. Okay. Now, again here, let's come back to our picture. So this 2 theta, this is a counterclockwise rotation. 2 theta is always measured from, so the 2 theta is always measured from that line CA to the phi axis. Okay, so we have our 2 theta is equal to inverse tangent of opposite over the adjacent side, and we get 76 degrees for 2 theta, so theta is 38 degrees, okay? And this defines the direction of the x prime axis in sigma 2, and it's associated with our principal plane. So I'm going to draw this here. Pretend that's even. Okay. And then what we're saying is that this here is the 31.2 psi. And then we have the negative 51 going in this direction. This here is my x. This is my x prime, and this is my 38-degree rotation. Okay? And now, so this is our principal plane, because that's where the principal stresses act. Okay. And now we can determine our absolute max. So this is the second part of the problem. So we already did principal stresses up there. Maybe I should move this down. Okay, absolute max shear stress. Okay, so again, we're going to redraw this circle. I'm just going to redraw it. Our center point would be, let's sit here. Okay. This is our positive sigma, positive tau. And then we know, of course, we know our principal stresses here. We know this is 31.2, and we know that this is 51.2. So from here, we have 2 options. We can either calculate what our absolute max is using the formula, or we can look at the circle, and both are fine options. Okay, it's really simple to figure out what the absolute is here. You don't even need to, I'll draw the 2 in-plane circles here. Yeah, it's so not, okay. Something like that. Okay, and it's already really easy to see the max, because the max is just going to be, what's the maximum value that this goes to? Well, it's the radius of the circle. And I'm going to show you that it's the same thing if you were to plug it into the formula I put for when sigma 1 and sigma 2 have different signs. It's positive 31, whoops. Get the same thing. That's our answer, okay? And again, we can get the average. okay? So since they're opposite signs, our max absolute shear stress here is our max in plane shear stress. So we don't need to worry about getting any different values here. So this is the same thing that's happening for all of this, okay? Oh, put a lot more room for that. Okay, so this concludes topic 8. If you have any questions, please post them in the comments on YouTube or shoot me an email and we can discuss it from there.